So let's start talking about streams. So uh, water in streams comes from precipitation, and the precipitation obviously comes from the evaporation of water. Most of the water in the atmosphere is evaporated off of the oceans and or transpired back through plants, right? So water evaporates off of the oceans, mostly in the tropics, and the water condenses to form that's clouds. That's the visible portion of water in the atmosphere. It gets blown maybe over land where it falls, condenses and falls as either rain or snow. You guys have all seen this a million times. You all know what's happening. The water hits the surface of the ground, and it can either run off in streams immediately back to the ocean. It can sink into the ground and be temporarily stored as groundwater, although it's eventually making its way downhill as well. Or it can be taken up by plants and released through the process of transpiration back to the atmosphere. Of course, it can be temporarily impounded in reservoirs, lakes, ponds, that sort of thing for a while. It can be stored in the body of organisms like plants, like trees mostly, or humans or cows or whatever. But by and large, it's just constantly moving around in this cycle, which of course is the hydrologic cycle. What we're going to focus on mostly in this class is what happens when the water infiltrates into the ground and exists as groundwater. But for the next couple of lectures, we'll talk about what happens a little bit more when it's on the land surface. So certainly that's the most visible and dramatic aspect of moving water, are rivers, streams, the erosion they cause, and the flooding that can result. So when we think about rain hitting the land surface, when the rain first falls from the sky and hits the land surface, it's not very efficient at moving across the land surface. If you have a little blob of water here, that's what that's supposed to be. That's a very, very tiny tree. This is a drop of water that's just fallen from the sky, and there it is. The water itself has a lot of what's called surface tension, and so it wants to sort of exist as its own little entity. It wants to just sit there. And you've seen this if you've ever driven in, as you all have, I'm sure, been in a car or something in the rain, and there will be little blobs of water that form on the windshield. They don't want to necessarily run off very easily, but if one does start to run off and starts to run down the windshield, whenever it hits another drop, the two drops will merge, and those two drops will continue further down. And the more drops they hit, the bigger the flow of water, the more you're able to continue that flow. So initially, individual drops of water that land on the surface aren't likely to go anywhere other than perhaps soaking into the ground for reasons we'll talk about soon. But if you begin to build up drop after drop after drop, you can get movement across the land surface, which is somewhat grandly referred to as overland flow. Which is we geologists would probably just call runoff. And as that water begins to slowly work its way across the land surface, it's not having a very easy time of it, right? Because it's got to go around individual blades of grass. It's got to move around rocks. I'm not drawing that very well, but hopefully you get the point. Those are roots. There's a rock. It's got to sort of snake its way across individual dirt molecules. And as a result, it's not moving very, very quickly. There's also a lot of friction between the water and the land surfaces it's moving across. However, eventually that water is going to make its way into a stream. And when the water makes its way into a stream, now it can really begin to flow much faster. And again, for reasons, I hate to keep saying this, but for reasons we're going to be talking about over the next couple of lectures. There are simple, basic explanations for why the water flows much faster in a stream than it does across the land surface. So for now, just take my word for it. And those small streams, now we're looking down from space here, so we're going to look we're going to look at a map. Those small streams, when they coalesce, just like drops of water on your windshield, once they coalesce, they have an easier time flowing. Each one of those little lines is a stream, and the scale here might be, you know, a couple of miles across. And so once they come together, they don't diverge. If anything, they just continue to coalesce. And so you have multiple streams coming together, and more streams coming together, and as a result, the stream keeps getting bigger and bigger and bigger. And this is referred to as a drainage network. So each one of those little lines we're looking at here is a stream, and you notice that there's a very similar, a very recognizable pattern. It's called a dendritic pattern. A dendritic pattern. And this kind of small streams flowing into slightly larger streams, flowing into even slightly larger streams, is a really very, very efficient way of distributing fluid or air or water. And if you look at the veins in a human body, you'll see a very, very similar sort of pattern, right? Big veins and arteries serve as the primary conduit for fluid, for blood, and then it gets transported into smaller veins, and finally down into the capillaries. And you get patterns that look a lot like this. There are a couple of ways for categorizing streams that look like that. And the two primary ways are the Strahler and the Shreve approaches. Methods, see if you can see that. Can you see that? Methods for categorizing streams. And I don't work enough in the business to know if one is preferred over the other, but you know, the Strahler method says, okay, any stream that doesn't have any other streams flowing into it is a first order stream. So first order stream has no tributaries. Tributaries. There we go. And so you can have two first order streams coming together, and when two first order streams come together, you get a second order stream. So a second order stream is the combination of two first order streams. And if that second order stream continues downhill and another first order stream comes into it, nothing changes. It's still just a second order stream. However, if over here we have a second stream, two first order streams that have combined to form a second order stream, and this second order stream and this second order stream merge, it now becomes a third order stream. So if someone is talking about a first order stream, what they're talking about is a very small, simple little stream that's not receiving water from other watersheds, right? It's got to be contained in its own little system. However, higher order streams, like second, third, fourth, fifth order streams, are representing the total flow of water coming from a variety of sources. The Shreve method is similar, but so we would still have first order streams here and here, but now it's more additive. So if a first order and a first order come together, you get a second order stream, that's the same. But now where this first order stream connects with the second order stream, now you get a third order stream. And if we have something that looks like this over here, 1, 1, 2, where the second order stream and the third order stream come together, you get, what do you get? It's additive, fifth order stream, right? So anyway, that's one way of categorizing streams, and not too hard, right? Okay, let's just talk briefly about the way streams look in general. We can think about, we'll call this stream characteristics. So we can think about streams in profile view and cross-section. And we can think about them in, we can think of this like side view, I think we were calling it before, profile view. And we can think of them in map view. So streams in map view are often, almost always, in fact they are, unless they've been impacted by humans, They are sinusoidal. They are curved. They migrate back and forth like this. And this happens naturally over time. And even if you were to go out and straighten a river and make it perfectly straight, so again, this is, just to be clear, this is north, just so that we recognize we're looking down from space. Even if you were to go out and make a stream perfectly straight, over time, it would again begin to develop these curves. Each of the bends, each bend is referred to as a meander. The rivers meander back and forth, and these bends, these meanders in the river, actually cause and reflect changes in water velocity. So to appreciate that, let's look over here for a minute. This is the side view. So water is flowing, let's say, from the page out towards us, right? And so where is the water going to be flowing the fastest here, and why is it going to change? Is it going to be flowing the same velocity everywhere? Well, it turns out that when water is moving, when water molecules are moving against each other, there's almost no friction between them. But when water molecules are moving against other objects, like the grass at the bottom or the rocks at the bottom of the stream bank, that's supposed to be grass, whatever, then there is friction. Likewise, there's friction between the water and the air up here. So you actually have slower velocities here. This is slower moving water, because the water is losing some of its energy to heat, believe it or not. Just like when you rub your hands together, you take some of the energy and you heat up your hands. As the water is moving over the rocks and weeds at the bottom of a stream, it's losing some of its energy to friction, and therefore is slowing down. So the fastest, likewise, when the air and the water moving past each other, you get a little friction and the water slows down. So the fastest water is right there in the middle, and then it gets a little bit slower up towards the top and along the sides. So water, for the same sort of reason, when we look down from space, right, we'd expect it to be flowing fastest in the center, and the arrow is pointing in the direction the water is moving, and the length of the arrow is reflecting the velocity of the water. So it would be flowing faster in the middle and a little bit slower towards the sides, because it's more of the water is rubbing against the riverbank there. So the water comes in like this and kind of bounces off and goes over here and gets deflected around. So as the water, which is moving in a pretty high clip, slams into the riverbank here, what's going to happen? Well, what's going to happen is the water is going to slowly over time begin to erode the sediment out from that portion of the bank. And that sediment is going to be then carried, it's going to be entrained by the water, and it's going to be moving over here, and the water again is going to be slamming into over here, picking up more sediment and bringing it down, and so forth. So the water is moving the fastest as it slams into the outside portion of these banks. Well, that also means then if the water is moving fastest on the outside of the curve, it's moving, so I'll write fastest here and fastest here. If it's moving the fastest on the outside of the curve, it's moving the slowest on the inside of the curve, here and here. So if the water is moving really slowly, it doesn't have the energy to keep the sediment that it eroded from the outer edge of the banks. It doesn't have the energy to keep that water suspended. And so what happens is, I'm just going to draw a big meander here, the water flowing this way. You get erosion on the outside edge of the river, and you get deposition of sediment on the inside edge. So water is being deposited here, and sediment is being deposited here, and it's being eroded here. This is called a point bar on the inside, because a sandbar will often be deposited there. And this is called a cut bank on the outside, because that's where the bank is, is being undercut by the river and being eroded. To see that in profile, you might see it if you've ever been canoeing or on a river. What you often see is the stream profile. Oh, my computer just died out, and I don't know if I'm still recording, so hold on. I don't know if that continued to record or not, but we'll see. So here we are. Here's some trees and some grasses and so forth. So the river is coming out of the page towards us, and as the water is slamming into the bank over here, this would be on the outer edge of a meander, it's eroding this sediment. So it looks like someone has cut underneath the overhanging bit of sediment. This is often held together by roots and things from grasses, and so it stays pretty stable even as the water cuts underneath it. Over here, you can see that the angle of the riverbed is much more gradual because this is all the sediment that's been piled up over here on the inside of the meander, the point bar. A couple of other things to point out really briefly before we stop this section. Let me see how long I've been talking. Pretty long. I'll take a break in just a second here. The other thing to know is that whenever you get a flood, so I'm going to go back to this thing again. Here's our stream. Whenever you get a flood, remember the water is coming out of the page towards us here. There's all sorts of sediment and everything that's being carried along by the water. As the water level rises, so that it now rises up out of its banks, what will happen is the velocity of the water slows down for reasons that we'll see, and sediment begins to pile up, often right on the edge of the riverbank. So that over time, the edges of the riverbanks have this little kind of little ropey high point on either side. And you can see it if this is the stream over here migrating down like this. This is again in map view. There'll be this kind of slightly elevated ridge running right along the sides of the riverbank. These are called levees. These are natural. The levees form naturally, these little elevated points. And so once they form, you have to get a bigger and bigger flood in order to breach the levees and have the water spill out onto the surrounding area. The surrounding area, by the way, is called the floodplain, this flat area on either side. Okay, so a long time ago, people recognized this and said, hey, the levees are kind of holding in the floodwaters. What if we build the levees up really big, artificially? Now it takes a really big flood before the water is going to spill out over the sides and impact our farms. And so this is one of the earliest forms of flood control, was building up these naturally formed levees.